Hi, everybody.
Hello, everyone. I'm pleased to introduce Ray Lee. He's graduated just last year from CMU, and he's now a first-year PhD at Stanford. And he's here to talk about random linear binary codes of smaller list sizes that then uniformly random binary codes. And this is joint work with Ray Lee.
All right, thanks for the introduction. It's great to be back, and thanks for having me. So as an outline of the talk, we're going to start by defining and motivating list decoding, and then I'll talk about this open question of constructing explicit binary list decodable codes, and then I'll state and sketch a proof of our main result, and if there's time, I'll discuss some corollaries. And I guess I don't intend for this talk to take the whole time, so definitely feel free to stop and ask questions. But before I do any of that, I'll give you a taste of what's to come by defining all the words in the title for you. So first, what is a code? A code is not a C++ or Python program, so just for the next 40, 45 minutes, forget that definition. A code is a set, and in this case, it's going to be a set of binary strings, so we'll call it C, and these strings will all have the same length n, and it will be over a binary alphabet. So we're going to think of these strings as elements of f2 to the n instead of just if you don't know what f2 is, it's the finite field of size 2. If you don't know what that is, think of it as the integers mod 2. Okay. And what is a uniformly random code? So it's what you think it is. We have a code, we want it to be a certain size, so we take that many elements independently, uniformly at random from f2 to the n, and that's going to be our code. There's this issue of what happens if there's collisions, but the effect of that turns out to be negligible, so we just ignore that. Okay, what is a linear code? A linear code, if we think of our code as a subset of f2 to the n, a linear code is a subspace. So whenever you see the word linear code in the talk, or I go like this with my hands, that means a subspace of f2 to the n. A subspace, if you don't know what that is, it just means if x is in your code and y is in your code, then x plus y, where you add the things point-wise, is also in your code. And the last term is something called list sizes. So it refers to something called list decoding. It was invented by Elias and Wozencraft in the 1950s, and it's something about how clustery our set of strings is. So formally what it says is if you take any Hamming ball and you intersect it with your code, no matter where your Hamming ball is, the intersection of that with your code is small. It's going to be at most some constant L. You can think of it as like 100. Okay. So this is a talk about coding theory, but if you strip away all the coding theory terminology, it's really a talk about a math problem. So let me show you what that means. So this title is saying random subspaces are in some sense less clustery than completely random sets of the same size. So now we'll see all this formally. Okay, so list decoding generalizes something you might be more familiar with called unique decoding. So in unique decoding, Alice has the message, and she wants to send it to Bob. But there's a noisy channel in between them, so she just sends her message directly. Bob might get the wrong message. So what does she do? She adds some redundancy. In this case, she repeats her message 3 times so that even in the presence of errors, Bob can still recover the original message. Okay, and formally, we define this as follows. So we're going to look at the set of things that Alice sends to Bob. These are the code words, so these are the strings of length 6. And it turns out most of the difficulty is in constructing a nice set of code words. So we're going to say this set of code words C, same C as the last slide, is P unique decodable if for every x in f2 to the n, C intersect the ball around x of radius Pn is at most 1. Okay, so first, what is B? xpn. I've written it up for you here. It's the set of all points that are within some Hamming distance of x. Hamming distance is the number of coordinates in which they differ. Okay, so this is saying that so think of x as what Bob receives. For anything that Bob receives, there's at most one code word that it could have come from, assuming Pn errors were applied to it. Okay, so that's how the definition corresponds to the picture. Okay, and list decoding is a very similar idea. So list decoding, Alice has a message, she wants to send it to Bob, she again adds some redundancy, and even in the presence of errors, perhaps a few more errors, Bob can maybe not recover the message exactly, but he can recover a list of messages that contains the correct message. Okay, and formally we'll write this as follows. Again, we're looking at the set of things that Alice sends, the code words. So we say C is PL list decodable if for every x in f2 to the n, C intersect the ball around x of radius Pn is at most L. So again, think of x as whatever Bob receives. So for anything that Bob receives, assuming that at most Pn errors were applied to it, there's at most L code words it could have come from. So L is going to be the size of the list that Bob returns. Or it's going to be at most L. Okay, so what makes a good code? So on one hand, we want our code to be robust. So we want P to be as large as possible. And on the other hand, we don't want to introduce too much redundancy. And the redundancy is something we quantify in the rate. So the rate, I've defined it for you here. R is log base 2 of C over n. And it roughly measures how big your code is. So the bigger the rate, the bigger your code is. Notice it's always a number between 0 and 1. So if C is all of f2 to the n, the rate is 1. If C is relatively sparse, the rate is close to 0. And so the larger the rate, the bigger the code, the less redundancy there is. And in this example, Alice has a 2-bit message, and she encodes it in a 6-bit code word, and so the rate is going to be 2 over 6. And so in coding theory, we want to optimize P and R. So we want P to be large, and we want R to be large, so what's this trade-off? And finding out this optimal trade-off is a big question in coding theory. And for list decoding, so we do that for unique decoding. For list decoding, we do the same thing, but also there's this other parameter L, and we also want to make L as small as possible. So throughout this entire talk, you should think of P, R, and L all as constants, and you should think of n as going to infinity. So sometimes during the talk, I might talk about codes, when really I mean a family of codes. Okay, so what do I mean by that? So notice that it's pretty easy to make a code with positive rate. You just need C to have 2 elements. But what we're really interested in is codes with a family of codes such that as n goes to infinity, the rate approaches some non-zero constant. So I might say constant rate codes when I really mean a family of constant rate codes. And if I say codes, I mean like a family of codes with these parameters. So anything else? Oh, the last thing I'll say on this slide is that you may have heard, if you've seen some coding theory before, there's different models of errors. There's adversarial errors, there's random errors. The definition I've given you here corresponds to adversarial errors. Okay. Now's a good time to ask questions if you have any. Okay, let's move on. Okay, so why do we care about list decoding? So there's 2 reasons. The first is that list decoding tolerates more errors than unique decoding. So in some sense, it's a more powerful notion. Okay, so what do I mean? So in unique decoding, it turns out if you fix a constant p less than 1/4, then there exists constant rate codes. So that means a family of codes whose rate approaches a non-zero constant that tolerates p and errors. Okay, and it turns out 1/4 is the best you can do. So if you assume p is bigger than 1/4, there's no constant rate codes that tolerate p and errors. On the other hand, there's something called the list decoding capacity theorem. I'll refer to it again. It's important for the talk, so I've written it for you here. But it says there exists rate 1 minus h of p minus epsilon codes that are p 1 over epsilon list decodable. Okay, so what is this h of p? So h of p is the binary entropy function. I've written for you here. And if you've never seen this before, you only need to know one thing about it for the talk, which is that it's always between 0 and 1, and for p strictly less than 1/2, this is strictly less than 1. So the upshot of this is that if you take p to be any p less than 1/2, and you take epsilon to be sufficiently small, then there exists constant rate codes that are list decodable with a constant list size. Okay. So somehow, if you take unique decoding and you relax the definition to say instead of every Hamming-Ball intersector code in 1 point, every Hamming-Ball intersector code in a constant number of points, then you can make your Hamming-Ball twice as large. Okay. And the proof of this is pretty simple. So you have a code of some rate that you want, so that means we know how many points are in the code. And so you just pick all these points uniformly at random, and then you just do a big union bound over all possible bad events, and you get what you want. There's nothing clever there. Okay, so it turns out what this actually says is the form I've written it for you here. So not only there exists, but a random code of this rate is with high probability list decodable with list size 1 over epsilon. Okay. And it turns out this 1 minus h of p is tight. So if you take any code of rate 1 minus h of p plus epsilon, then the best list size you can get just by a simple counting argument has to be exponentially large in n. So somehow this 1 minus h of p is a very sharp threshold. If you're slightly above it, your list size needs to be exponential. If you're slightly below it, you can get your list size to be constant. Sorry, I think there was one more thing I wanted to say. Yes, so because this 1 minus h of p kind of comes up a lot, sometimes throughout the talk I'll say a capacity achieving code. So when I say a capacity achieving code, I mean a code with this rate 1 minus h of p minus epsilon. Oh, and so I guess looking at the picture, what this says is if you take p to be 1/2, then if you have any constant rate code, that means the best list size you can get is exponentially large. So that's the first reason. The second reason we care about list decoding is it has a lot of natural applications. I'm not going to go into all of these, but there's kind of two flavors of them. The first one is more direct application, where if you look at constructing certain, say, pseudo-random objects or objects in complexity, like hardness amplifiers, expanders, extractors, then you look at them and syntactically they're the same question as some question about list decoding. Maybe for these other objects you care about different parameters, but they're the same question, and sometimes better list decodable codes give you better hardness amplifiers, for example. There's also sort of applications where you use list decoding as a tool, so you have some problem you want to solve, and you take some explicit list decodable code and use it for that. Okay, but that's all I'll say about the applications. Okay, so list decoding is a powerful notion. We can use it to correct twice as many errors as unique decoding, and it has a lot of applications. But for any of this to matter, we need explicit list decodable codes. So notice that this is the best possible rate versus p trade-off we can get, but we get it with a completely random code. So that's very non-explicit. You need exponential and n many bits of randomness. So that's no good. So we want so it's an open question to find explicit, efficient, rate 1 minus h of p minus epsilon list decodable codes. Okay, so what do I mean by explicit? This is sort of a loose notion. One way you can think about it is you can produce some description of your code in polynomial time. So for example, if your code is a linear code, you can produce the generator matrix in polynomial time. The more important notion here is efficient. So remember in the communication setting, we had Alice takes a message, adds some redundancy, and Bob takes the received word and decodes it. So efficient means that the encoding and decoding functions can both be computed efficiently. Okay, and so remember we define list decoding as just a combinatorial property of the set of code words, but really the end goal, as you see here, is to find codes where you can do this encoding and decoding efficiently. But this talk is mostly going to be about the combinatorial properties of this set. Okay. So some of you may have seen this analogy before. So answering this open question is analogous to finding hay in a haystack. So we have our universe, which is all codes of this rate. And we know by the list decoding capacity theorem that a random one of these is list decodable. So so we have a haystack, but somehow it's hard to go into this haystack and pick out like one explicit list decodable code. Okay. So just as a disclaimer, so you're not disappointed later in the talk, we don't answer this question, but we do answer a question that I guess helps us understand this better. Okay, but there are some things known. So if you here we're taking codes to be over f2 to the n, but if you allow your codes to be over a larger alphabet, then there are known list decodable codes with good list decoding algorithms. So in 1999, Guruswami in Sudan showed that you can list decode Reed-Solomon codes efficiently up to some radius. And in 2008, Guruswami and Rudrak invented folded Reed-Solomon codes. And the important thing about folded Reed-Solomon codes is that they achieve capacity. So here we have for binary codes, the optimal p versus rate trade-off is p versus 1 minus h of p. And when you allow larger alphabets, there's a similar optimal trade-off you can get. And folded Reed-Solomon codes achieve that trade-off for larger alphabets. Right, so in some sense, for larger alphabets, the answer to this question is known. Okay, but for binary alphabets, we don't know any explicit efficient codes. And even so, in the capacity theorem, we got the list size down to a constant. I think even if you relax this and say we want L to be sub-exponential, we don't know of any codes. There's a nice survey by Guruswami on the progress on this problem. So on one hand, we have completely random codes, which are optimally list decodable. And on the other hand, all the explicit constructions of binary codes we have are not optimally list decodable. So they don't achieve this capacity. So if you're a coding theorist, a natural question you might ask is, can we somehow make the random construction less random, so introduce some more structure and still show these codes are optimally list decodable. So if you're a coding theorist, the natural thing to consider is random linear codes. Okay, so a lot of your favorite codes like Reed-Solomon codes, Hadamard code, etc. These are all linear codes. And linear codes use less randomness than completely random codes. These use exponentially many bits, but linear codes use polynomially many bits of randomness. Okay, so what is a random linear code? I swept that under the rug earlier, but a random linear code, we're going to think of it as the span of independent random vectors. So span means you take every possible linear combination of them. You can check that if you have this many vectors, then the rate is R, what we want it to be. And there's this technicality of like you're going to choose these basis vectors independently at random. And there's this technicality of what happens if there's linear dependencies among them. But that turns out to happen with exponentially small probability. So we just pretend it doesn't happen. It has a negligible effect. Okay, so what's known about the list decodability of a random linear code? So a random linear code of this rate, so we know that it's list decodable with constant list size, just by modifying this list decoding capacity theorem argument. Okay, this is by Ziablov and Pinsker in 1981. But somehow this is different from this linear dependence in 1 over epsilon. So in 1991, Elias asked explicitly, can we show that random linear codes are list decodable with list size linear in 1 over epsilon? In 2002, Guruswami, Håstad, Sudan, and Zuckerman made progress on this problem by showing that there exists codes of rate 1 minus h of p minus epsilon that are list decodable with list size 1 over epsilon. So this really is 1 over epsilon, the same 1 over epsilon, not some O of 1 over epsilon.
It's really like bigger than 0, not like peak probability.
Yes, yes. So they showed there exist codes.
So just existence.
Just existence, yeah.
Like local lemma type bound.
Yeah, something like that. Well, you'll see. And in 2011, Guruswami, Håstad, and Koparty showed that these codes, that random linear codes are with high probability list decodable with list size 1 over epsilon, or linear in 1 over epsilon. The caveat about this result is that this constant blows up to infinity as p gets close to a half. So there's a little bit of a gap to close, but in 2013, Mary Wooters closed this gap by showing that even if p is arbitrarily close to 1/2, that there's some uniform constant that you can bound the, constant in front of the 1 over epsilon, the list size. Okay, so what have we done? So we had our universe, which is all codes of this rate, and we said it was a haystack, and we sort of shrink our universe to linear codes. Then we know that we still have a haystack. We know most linear codes are also have this list decoding property. Okay, and just to make sure I'm being honest with you, there's also another construction of random linear codes that are called concatenated folded Reed-Solomon codes. These are even more explicit than just random linear codes. They're a more structured kind of random linear codes, and they also achieve this list decoding capacity. So I'm just mentioning it, but I think random linear codes are still kind of an interesting question in themselves. These are also not completely explicit. They use slightly fewer polynomial many bits of randomness. So in some sense, we're done. But there's two things that are kind of unsatisfying about this state of affairs. The first is that for the existential result, we could get a list size of 1 over epsilon. And for these high probability results, we get some larger constant. So like, I guess, can we bring the constant down? Okay, but you might say, oh, who cares about the constants? The more unsatisfying thing is that for these, to get this qualitative result that random linear codes sort of are as list decodable as completely random codes, you need to patch together two very different arguments, like these two arguments. And so the question that we started with was, can you find one argument that kind of unifies these? And because given that this is just a simple union bound, can we find some simple argument for random linear codes as well? And we sought to answer this question, we did, and as a corollary, we were able to improve the list size, the constants as well. Okay, so the title of this slide is the title of the talk, so I'm going to replace it with a picture. So remember our mathematical question is how does the clusteriness of a random subspace compare to a completely random set of the same size? And our main result is that a random subspace, so a random linear code, is less clustery than a completely random set. Okay. So on this slide, I think before, it didn't really matter whether p or epsilon, like how p and epsilon are varying, but for this slide, you should think of p as fixed and epsilon as going to 0. And okay, so what do we know about a random code that achieves this capacity? What's the list size? So some of these results you've already seen. So for a completely random code, you can get list size 1 over epsilon. And by the two results we mentioned on the previous slide, you can get list size that is constant over epsilon, so linear in 1 over epsilon. And our result is that you can actually show that random linear codes are list decodable with list size h of p over epsilon plus 2. The plus 2 is just that comes out for technical reasons. But the key is that h of p, remember, h of p is less than 1 for p less than 1/2. So the list size bound that we get for random linear codes is strictly smaller than the list size you get for uniformly random codes. Okay, so that's our main result. But you might object that this doesn't give us the picture because you know, the 1 over epsilon that we got for the list size of a completely random code was just by a simple union bound. And you might say, well, what if you were sort of more clever, you did some other probabilistic argument, and you showed that you can actually get list size like log 1 over epsilon or something. But it turns out this is not possible. So a result by Guruswami and Narayanan showed that the list size, the best list size with high probability is always at least has to have a linear dependence in 1 over epsilon. And we actually tightened this result to say that it not only has to be linear in 1 over epsilon, but the constant in front of the 1 over epsilon has to be 1. So this is an example where like this 1 is really the best possible. You can't replace it with a 0.99. And for those of you who are interested in math, this is not in our paper, but you know, if I worked it out sort of by hand, the 1 over epsilon as epsilon, if epsilon is sufficiently small, really is 1 over epsilon. So this is telling us that the best list size you can get for a uniformly random code is concentrated around 1 or 2 numbers. And then the last thing is that there's also a lower bound of 1 over epsilon for random linear codes. Okay, so what have we said on this slide? Well, we said we have a lower bound for the list size of uniformly random codes, and we have an upper bound on the list size of, a lower bound on the list size of uniformly random codes and an upper bound on the list size for random linear codes. And there's a gap here, so we really do get the picture in some high probability sense. Okay, so now is a good time to ask questions if you have any.
Don't have a much lower bound for random linear?
Yeah, so I guess, yeah, we don't.
So the bit you were saying about being concentrated around 6 points, you're saying the like total number of, like, if you sum up all the list sizes, then almost all the lists are on a couple points?
Okay, so what do I mean by concentrated around 1 or 2 numbers? It's saying if you take a uniformly random code, and let's take the smallest L you can make it. So smallest L such that it's PL list decodable. Whatever this best L is over the randomness of the code, the L is concentrated around 1 or 2 numbers.
So I guess you only get separation if P is like less than a half between these?
Yes, so we said that if P is bigger than a half, then you can't get constant rate list decodable codes. Like, yeah.
So is it hard to check if I give you a code, is it hard to check how big the lists are?
As far as we know, yes. Otherwise, you could take our result and make it like an explicit efficient. Yeah. Other questions? Okay, so now I'm going to go on to the proofs. I'll go over a proof of our upper bound result, and maybe actually right now I'll just say one sentence about the lower bound. So the lower bound, Guruswami and Narayanan proved it by using a second moment argument, and we basically just used the exact same argument, but one of the places we tighten one of the bounds that they have, and it brings us to 1 over epsilon. Okay, so good. Okay, so how does the proof go? So I'm going to start by giving you the proof that Guruswami, Håstad, Sudan, and Zuckerman gave, that there exist linear codes that are P1 over epsilon list decodable, and then I'll show you how we modify it. Okay, good. So remember, this is the definition of a random linear code, and this is our goal, to find like C that satisfies this property. And so the cleverness of their argument is by looking at this potential function. So we're going to let L of x be the size of C intersect the ball around x of radius Pn. So if you look at the definition of list decoding, what we want is that all of the L of x's are at most 1 over epsilon. So if we show all the L of x's are at most 1 over epsilon, then we get list decoding. And we define S of C to be the expectation over a uniformly random x of 2 to the n epsilon L of x. Okay, so what in the world is this? So L of x is always at least 0, so S is always at least 1, just by, by working it out. And if C is, for example, all of f2 to the n, S is doubly exponential in n. So that's enormous, and we can't control that. And if S is at bigger than 2 to the n, then you can show that your code is definitely not list decodable with list size 1 over epsilon. On the other hand, if S is at most 2 or any constant, then you can show that our code is list decodable with list size 1 over epsilon. And so the basic idea of the proof is we're going to start with C to be just one element, so the span of empty set, and then we're going to take the span of one vector, so it's two elements, then the span of two vectors, three vectors, and we're going to keep adding vectors to our basis elements to our code, and we're going to watch how this potential function increases as we add these vectors. And our goal is that we want to show it increases sufficiently slowly so that by the time we get to the end, our potential function is still less than, say, 2, and then we get list decodability. Okay, so that's the basic outline. Okay, so how are we going to do that? We want S to be 2 at the end. So the key idea of this potential function is the following fact. So I know there's a lot of symbols, so I'll walk you through it. So let's suppose that we have chosen I basis vectors so far. Then let's suppose we want to add one more dimension to our code. So we add one more basis vector uniformly at random. Then it turns out that, so we fix the I basis vectors and we add one more. How does the potential function grow in expectation? So it's going to approximately square. Okay, so the way you should think about this is S is going to be 1 plus delta, so 1 plus something small for most of our talk. So if S is 1 plus delta, what's S squared? It's going to be about 1 plus 2 delta. And so what's this going to look like? Well, you can work out just by hand that if you take a code with one element, then the potential function is this 1 plus 2 to the minus n, 1 minus h of p minus epsilon. And the exponent should look a bit suspicious. Okay, so what does this fact tell us? This fact tells us that in expectation, we pick a uniformly random basis vector, then the potential function is going to square, or the lower order term is going to double. And then in expectation, the lower order term is going to double again, and then it's going to double again, and then if it keeps doubling, then if we choose our parameters carefully enough, then it will be less than 2. So then sort of in expectation, the basis vectors we choose should give a list decodable code. Okay, why does this square? I have a backup slide that gives a proof of this if you want. No.
Is there any intuition for it?
Okay, so you can think about when your code is really sparse. So then, I guess, so when your code is really sparse and you take, okay, so if your code is one element, then you have a Hamming ball where everything in that contributes 2 to the n epsilon, and everything outside of it contributes 1. So if you just have one point, a bunch of points, a bunch of the L of x's contribute 2 to the n epsilon, a bunch of them, the rest contribute 1. And then if you have 2 points, then if the Hamming balls don't intersect, then you get 2 Hamming balls that each contribute 2 to the n epsilon, and the rest contribute 1. So kind of the lower order term, you get twice as much contribution to the lower order term. So somehow, when the code is sparse in expectation, the thing is doubling. Other questions? Okay. So the idea of Guruswami, Håstad, Sudan, and Zuckerman is that, well, if this happens in expectation, then surely there exists some choice of B1 such that the first line holds, and there exists some choice of B2 such that the second line holds, and so on. And then there exists, so that means there exists some choice of basis vectors such that the potential function grows slowly. So there exists some choice of basis vectors such that you get a code that's list decodable. And that's the entire proof. It fits on a page. Okay, so where do we improve this? All right, so the first thing I said was that if S is at most 2, then our code is P 1 over epsilon list decodable. But it turns out this S being at most 2 is a pretty strong condition. So if you combine that with the fact that we're taking a linear code, you can actually bring this list size constant down to h of p over epsilon plus 2. Okay. But perhaps the more substantial improvement is that we make this high probability. So to remind you, we have this kind of, ideally, this is how the potential function grows with a lower order term doubles at every step. And so Guruswami, Håstad, and Zuckerman showed that there exists B1 at every step. But we actually showed that if you apply Markov's inequality in the right way, then you can actually show that each of these steps, sort of the potential function grows as we want it to with high probability. Okay. So basically, we choose a good B1 with high probability, and then condition on B1 being chosen correctly, we choose B2 with high probability. And if you do a union bound, you say that every step succeeds in total with high probability, and so you get a high probability result. Okay. And that's how we improve, and that gives the entire high probability result. Are there any questions?
how you get a high probability result out of Markov.
Ah, good. Okay, so if you apply Markovs in like the simple way, so we know that S. So if you apply Markovs in the simple way, you know S is at least 1, which means that you get something like the probability S is bigger than 4 times that thing is at most 1/2 or something, right? So that means like the probability that the lower order term quadruples or more is at most 1/2. So that's not good enough because we really want the lower order term to double. So what you can show, sorry. So I guess you get that the expectation of S of C, I guess the next one is, this is at most like 1 plus, so we're going to let S of C be 1 plus delta. Then expectation of S of C is 1 plus 2 delta plus delta squared. So if you just applied Markov with knowing that's bigger than 1, that's not good enough. So what you can show is that S of C is in fact or C plus 0b is always at least 1 plus 2 delta. So this always holds. So we know it's always at least 1, but in fact we also know it's always at least 1 plus 2 delta. And if you apply Markovs with this, now you're applying it on the third order term. And since you apply it on the third order term, then you get that the first and second order terms are what you want it to be. And showing this is just you can use like rearrangement inequality or something fairly simple. Yeah. Other questions? Okay, so as a corollary of our technique, we get a few things for free. So this is one of the corollaries. So it says a random linear code of this rate is with high probability for every L, the number of balls that intersect our code in at least L points is at most 2 to the n times 2 to the minus n L epsilon. Okay, so the way you can think about this is if you replace for all L with just L equals 1 over epsilon, this gives us a list decoding result. So this says our code is with high probability, list decodable with list size 1 over epsilon. Okay, and on the other hand, if you think about the case where L equals 1 and 2, so if L equals 1, you can show that this should be approximately equality. And this is saying that the number of balls that intersect our code in at least 1 point is like somehow exponentially bigger than the number of balls that intersect our code in at least 2 points. And this is consistent with some intuition that we have about random linear codes in, I guess, the binary symmetric channel. So we know random linear codes achieve capacity on the binary symmetric channel. And that basically says that if you take a random linear code and you pick a code word, you apply Pn errors to it at random, then over the randomness of these Pn errors, this point that we get is close to 1 code word with high probability. It's not close to 2. And that's what this is saying here, that most points that are close to at least 1 code word are close to exactly 1 code word. So somehow this result kind of generalizes some of the intuition that we have that, I guess it generalizes our result and generalizes this intuition about random linear codes achieving capacity on the symmetric channel. Okay, and the second thing we get for free is the list decodability of rank metric codes. So what I've been talking about here so far are codes in the Hamming metric. So this is when code words are strings, and the distance between 2 code words is the number of coordinates in which they differ. But you can also take codes where your code words are n by n matrices, and the distance between two matrices is the rank of their difference. And you can check that this is subadditive, so you get a metric. And so there's a similar list decoding capacity theorem that you can get for rank metric codes, and as you might guess, a random code gives you the best possible. And okay, so if you take a uniformly random code, it gives you a list size of 1 over epsilon. And a random linear code, if you kind of modify this argument in the same way this argument was modified for the Hamming case, you get list size exponential in 1 over epsilon. So you might ask, can you get linear in 1 over epsilon list size? And Guruswami and Resh, so Venkat and Nick, who is a student here, they showed that random linear codes give a list size that's linear in 1 over epsilon, but again, this p blows up, the constant in front of that 1 over epsilon blows up as p goes to infinity. And so our result is that if you take a random linear code, the list size is with high probability, you can get it to some constant less than 1 over epsilon. And so one caveat about, I guess, this result and the other results that I mentioned is that this result by Venkat and Nick, it works for codes over larger alphabets, and ours only works for binary alphabets. And similarly, the two results by GHK in 2011 and Mary Wooters in 2013, those work for larger alphabets, but our result only works for binary alphabets. Okay, so I can conclude now. So some open questions are, can you improve our result to not only work for binary alphabets, but to work for codes over arbitrary alphabet or codes over larger finite fields? And there's this major open question of explicit, efficient, list decodable, capacity achieving list decodable codes. Okay. So to summarize, we started by defining list decoding as a useful generalization of unique decoding. So list decoding tolerates twice as many errors, and it has a lot of useful applications. Then we talked about this open question of constructing explicit, efficient, capacity-achieving list decodable codes. So de-randomizing the capacity theorem construction. And then we talked about our main result that random linear codes are have smaller list sizes than completely random codes of the same size. So in terms of the mathematical question, random subspaces are less clustery than random sets of the same size. And we talked a little about the proof, which is by considering an appropriate potential function. Okay, that's it. I'm happy to take questions.
Questions?
So one of the big goals that you're mentioning is making, explicit ones of these. And I was wondering, does this sort of result changing, previously had some constant that was terrible and now the constant is better than the random code, does this help towards that goal? Or is this,
So I guess, does improving this constant, does it help towards that goal? Maybe in the most direct way, probably not, but I guess maybe the fact that the potential function gives a high probability result, maybe you can use that to construct explicit codes, maybe, I'm not sure.
I guess as a whole, I guess you can't really calculate the potential function.
Yeah, exactly.
You could try to approximate it by sampling some points and then picking the next basis vector that.
Yeah.
Does that work?
Well, we tried it a little bit and we weren't able to get anything, but I mean, yeah.
Yeah, sorry if you already said this, but so have people had much success in de-randomizing, say not even list decodable codes, but just L equals 1, regular codes?
So what's known about unique decoding, right? So I think for unique decoding, the optimal, so here we know the capacity is P versus 1 minus H of P. We don't even know that for uniquely decodable codes. There's a lower bound, which is the Gilbert-Varshimov bound, and then there's this upper bound. There's some upper bounds like Elias-Basalgo or some LP bound. So, but there's definitely a gap there, and that's one of the big questions.